Section 5.4, this statement of fundamental theorem of calculus, part 1, applies to continuous functions, right? But in fact, it can be used to integrate functions whose the number of discontinuity is just a finite number of holes and jumps. And so let's do an example of that. Look at this function. How many jumps and holes do you see? I see one over here at C, and I see another one at D. At C there's a hole, at D it's a jump, at E is another jump. So it's not continuous in 3 places. Oh, that corner actually is continuous, right? You go through it and without any discontinuous movement, and so that one is a continuous one. It's just not differentiable. And again, integrals are a lot less fuzzy about functions that the derivatives are. And so now, how do I manage this with fundamental theorem? You have to break it down into pieces that are continuous. So look at this. I can start from A to C. See, A to C, that piece is continuous. Then I can go from C to D. From C to D, the function is continuous. Then I can go from D to E. Again, D to E function is continuous. E to F and F to B, they're all continuous. I could have put this together as well, but then I realized that when there's such corners, I can break them down into 2 elementary functions. So that's another thing too. And so not only for the points of discontinuity, to make the functions elementary, to avoid, let's say, absolute values, that sort of things, you can also break down the function into pieces. So you can evaluate each of the 4 integrals separately. And so the first one over here is going to be the pink area. Then the second one is going to be the teal above minus teal below. And then you will have the third one is the orange. Then the blue is the 4th one. And then the brown is the 5th one. And then you add them all together, and each piece uses the fundamental theorem of calculus. Basically, you take you evaluate each piece using the fundamental theorem, and then you add them all together. And that is a very strong tool that takes care of a lot of material for us. So again, there are ways, some of those infinite discontinuities also can be integrated, but it's not using the fundamental theorem calculus part 1. We're going to use other facts with that, other theorems with that, and that happens in Math 126 or Calculus 2. So now let's do an example. The velocity function in meters per second for a particle moving along a line is v of t equal to 3t minus a. Find the displacement of the object from time t equal to 0 to time t equal to 4. Find the total distance traveled from time t equal to 0 to time t equal to 4. And so how do we go about doing this? So what is the displacement? Displacement is derivative of displacement is the velocity. So velocity is antiderivative of displacement. And so when I'm taking the antiderivative of the other way around, then I said wrong. Displacement, derivative of displacement is velocity. So antiderivative of velocity is displacement. So integral from 0 to 4 of v of t d of t dt is going to give me the total displacement. If you remember, we did the antiderivative. Then antiderivative had in previous section we did antiderivative of v of t. Antiderivative had a constant. Then we evaluated at 2 endpoints, and the constant kind of simplified out. Now, by using fundamental theorem, you don't even have to worry about that constant anymore. So you can compare this question to very similar questions in section 5.3 and see the difference. So when you take the antiderivative, so then we calculate the integral and then again, term by term antiderivative, it gives you 3t, gives you 3t squared divided by 2, and 8 gives you 8t, and then you plug in the two endpoints and you find -8, which means that the particle has moved back 8 units, 8 meters basically. And so this gives me the net change. Now, but when we talk about the total distance traveled, if I go forward and if I go backward, it's just what you're basically, if you're walking around back and forth, what does your pedometer tell you? Or what does your, if you're going with a car, how your the distance that the car is showing. That one is a little different from just net change in the position. That's actually the total distance traveled, and that comes from the basically the net change in the absolute value. I'm sorry, it comes from the accumulative absolute value rate together, basically, rather than just the how the displacement comes from. So you take the antiderivative of the absolute value of the rate, and then this gives you the total amount that you traveled, the total distance that you traveled within this time interval. But here's the thing, this v of t is basically positive between, negative between 0 and 1/3, and it's positive between 1/3 and 4. And so the absolute value of it is going to be basically negative of v of t between 0 and 1/3 and positive vt between 1/3 and 4. So that's what you do. You break it down basically. So I know that v of t, here's 1/3, here's t, here's a v of t, and I know that v of t is -8. This is the function v of t. And so between here to here, if I'm taking the absolute value, and then let me draw the absolute value function. So the absolute value of v of t would look like this, right? This v shape. So I know that I have to break it down into two pieces, 0 to 1/3 dt plus 1/3 to, what's the last point? 4 dt. In this side, the absolute value and the function are the same, so you put in v of t. Over here, the absolute value and the function are the opposite of each other, so you put in negative v of t. And then you compute, which is going to be this, just regular things. You find the antiderivative of each piece, and then you evaluate at endpoints, and you get 40 divided by 3. And so that's the total distance that your pedometer is going to show. Again, that picture that I drew over there, this is the y equal to 3t minus 8. And when you're finding the displacement, the area under is a negative the area under plus the area above. When you're finding the total distance traveled, you're adding the two of them together. And so two different explanations that you saw. Now let's do the eye clicker question. A silkworm crawls back and forth along a straight line, trailing a thread of silk behind itself as it crawls. Its position at time t is given by x of t, starting at t equal to 0 and ending at t equal to 10. What is the total length of the thread of silk produced by the worm? And so I suggest stopping the video and coming back to it. So this question is again one of those things that the silkworm is going back and forth, right? Going this way and going that way. And so if I take the integral of the if I take the integral of the rate, which is the velocity, would give me the change in position. If I take the integral of the absolute value of the rate, then it gives me the total distance traveled, which makes sense with the amount of silk produced. So I have to do absolute value and I have to do rate. Which one? This one has absolute value, and this one has absolute value. That one is the position itself. So that's not the rate, but this one is the rate. So this is the answer.